Good morning, everyone. We are the team from Nanyang Technological University, and today we present our coursework on Titanic, Data Governance and Modeling. I'm Zihao from the NTU AI program. Our team consisting of Cao Zihao, Sun Ming, Xu Ke, and Jiang Huajian. Focus not just on prediction, but on the rigorous process of data quality, preparation, and building interpretable models. To ensure a structured approach, we followed a 5-stage pipeline shown here. We started with data quality checks to understanding maintenance, followed by outlier treatment to stabilize distributions. Then, we moved to feature engineering to extract the domain signals, followed by modeling, and finally, visualization for evaluation. Let's dive into the data. Our initial profiling reviewed distinct missing value patterns. While age has 177 missing entries, cabin has a significant gap with 687 missing values. The heat map on the right suggests that the missingness in cabin is likely structural, perhaps indicating lower class passengers without assigned cabins, rather than random. Visualizing the numeric features via a pair plot gave us our first clue about survival. The hue distinction between blue and orange shows that higher class passengers paying higher fares had a clear survival advantage. Conversely, large family counts seem associated with lower survival rates. Zooming in on age, the density plot confirms a tragic reality. Children had a noticeable survival advantage, while the elderly were less likely to survive. On page 7 and page 8, when we break this down, we see that children had a nearly 58% survival rate. However, the most striking insight comes from combining age, sex, and class. Females in first class had a 96.8% survival rate, whereas males in the third class had only a 13.5% chance. This confirms that women and children first and social-economic status were the dominant factors. On page 10, the violin plots show the age density across classes. We notice that the age distribution is wilder in the first class compared to the third class, which is skewed younger.
Hello, I'm Sun from NTU AI. Following the initial exploration, I will discuss how we prepared the data for modeling. Raw data is rarely model ready. On page 11, you can see the box plots for fare and age highlight significant outliers. Extreme values that can distort model coefficients. To handle this without discarding data, we applied winsorization. By keeping the values in the first and the 99th percentiles, we compress the extreme tails. Comparing this page and this, you can see the distributions become more stable and representative, reducing the model's sensitivity to noise. Beyond outliers, we address the skewness. The original file distribution is highly right-scaled. Parametric models often assume normality. We applied the Young-Johnson transformation, which effectively normalized the distribution, making patterns more discernible for the algorithm. Similarity for the SIBSP feature, the original skewness was 3.70. Since this data contains zeros, we shifted the data by +1 and applied a box-Cox transformation. This reduced the skewness and helped linearize relationships between family size and survival, preparing a solid foundation for our feature engineering. Okay, this is my part of presentation. Thank you.
Hi, I'm Xu Ke. Next, I will walk you through the feature engineering section. First, in terms of family, we created the feature of family size by combining the number of siblings, parents, and the passengers themselves. As shown in the feature, there is a clear nonlinear pattern. Passengers from medium-sized families, like 2 to 4 people, had the highest survival rate, while those traveling alone and those from larger families had lower survival rates. We also considered the fear per person and compared the distribution of the fear per person between survivors and non-survivors using a KDE plot. The descent plot shows a thicker right tail for survivors, which confirms that individual spending power rather than just the total fear is a strong predictive indicator. We extracted a new feature title from the name field, which we used as a proxy for social status. As shown in the chart, the survival probability for medium and miss was relatively high, while that for Mr. was extremely low, a pattern that reflects the rescue protocols of the time. We also consider the impact of imbalanced feature counts. The size of the error bars shown in the feature quantifies the uncertainty of these categories, reminding us to exercise caution when handling real labels. Survival rates varied significantly across different dig levels, and severe data missing lead to a high degree of uncertainty. This feature should therefore be excluded during model training. The heat map of full feature correlations shows that the survival rate is closely correlated with features such as passenger class, sex, and fear. The variables constructed through our previous feature engineering have also enhanced interpretability. Then we focus on the top 10 most important features. We can see that sex female and title misses have strong positive correlations with survival, while sexy male and title Mr. are strongly negative. And interestingly, P-class shows a negative correlation, meaning as the class number goes up, survival goes down. To understand how the model thinks, we used a random forest. The feature importance plot ranks fear and age class interaction as top predictors. However, the sharp summary plot offers deeper insight. It shows that being male or having the title Mr. pushes the prediction strongly towards death, while high fear pushes towards survival. This interpretability is crucial for trusting the AI's decision-making process.
Good morning. My name is Zhenghua Jian. I'm from NTU AI. I will conclude our modeling results. First, does data governance matter? Look at this page. Comparing the baseline, the blue one, with our full feature preparation, the orange one, we see that, well, accuracy is similar, but the ROC AUC increased to 0.57 and recall improved significantly. This proves that our feature engineering helped capture more positive curve without sacrificing precisions. And we evaluate two models. The first is logistic regression and another is decision tree. For the logistic regression, we turn the regressionalization's parameter C. We found stability around C equal to 1. And the best region is around C equal to 1 with accuracy 0.27 and ROC AUC 0.71. And the next page is confusion metric and ROC curve. You can see the two pictures. The confusion metric shows the model favors correct negatives with some false negative remain. And the ROC curve shows a strong stability with AUC 0.57, which indicates a good ranking ability and supports the use of ROC AUC as a stable comparison metric. And the next model is decision tree. And the depth value shows a clear trade-off. Depth for yields the strongest balance with ROC, AOC around 0.55 and accuracy 0.519. And the deeper tree shows decline ROC AOC indicates overfitting risk. And well, the final model. Comparing the final model on the holdout set, the logistic regression achieved AUC of 0.57, slightly outperforming the decision tree's ranking ability. Also, the tree has marginally higher raw accuracy. The confusion metric shows the correct predict 95 non-survivor and 50 survivors with a balanced correct rate. And to conclusion, we have 3 points. The one is data preparation is very important. Cleaning and engineering feature like title, like family size, significantly stabilized more model performance. And the second is model selections. Logistic regressions proved more robust for the dataset compared to the sensitive decision tree. And the third is real-world implication. This analysis goes beyond the tiny. It demonstrates how interpretable AI can be used in sectors like insurance, like healthcare. We understanding why a decision is made is just as important as accuracy of the decision itself. And it is all of our report. Thank you for listening.